Let us now look at some aspects of atomic and nuclear physics. So first thing we want to look at is the photoelectric effect. It was first observed by Heinrich Hertz and then explained by Einstein, and Einstein actually won the Nobel Prize for it. We know Einstein for relativity, but the theory that he won the Nobel Prize for was this photoelectric effect. So the photoelectric effect says that light of sufficiently high frequency striking a metal surface can eject electrons from the surface. So one thing to note here is that it's not the intensity of the light striking the metal that ejects the electrons, it's the sufficiently high frequency. So what is sufficiently high? What does that mean? Well, it means that each metal that we're shining light on has something called a threshold frequency. So the frequency has to be that the light has to be higher than this threshold frequency so that the electron can be loosened up by the light and then possibly even ejected. So the important thing about the photoelectric effect is that it is proof that light, which we thought of as a wave before, can behave as a particle. And the particle of light is what we call a photon. So the energy of this particle is then h times f, where h is called the Planck's constant, and it's equal to 6.63 times 10 to the negative 34 joules second. So the energy of a photon is Planck's constant times the frequency. So the equation for the photoelectric effect is HF, so that is the energy of the incoming light, is equal to this W, which we call the work function, and that's the energy required to loosen up an electron in the metal, plus the kinetic energy given to the electron. So if we look at a metal surface, here we have a photon, so that's the light. The symbol for the photon is gamma, it's a gamma ray. So it strikes the metal and it loosens up an electron, and that electron will then get ejected from the metal. So then, by conservation of energy, we'll say that the energy of the incident photon is equal to the work function, so that's energy required to loosen up the electron, plus whatever kinetic energy the electron will acquire. So the minimum energy necessary to loosen up this electron, to free it from the metal, is going to be equal to the energy of the incident photon. And then if there is extra energy, then that electron can even acquire some sort of kinetic energy. Now, this work function is related to the threshold frequency. So this work function is going to be h times the threshold frequency. All right, let's now look at energy levels. So we know from the Bohr model of the atom that electrons have stable energy levels that correspond to specific orbits. But if an electron will acquire energy from a photon or give up energy from a photon that's sufficient to jump between orbits, then the electron can move up to a higher orbit or a lower orbit, so it can acquire more energy or less energy, and that all has to do with emitting or absorbing photons. Let's look at the nuclear binding energy and the mass defect. So nucleons are held together inside the nucleus by the strong force. The binding energy of the bonded system inside the nucleus turns out to be lower than the energy of the unbonded constituents. So if we compare the energy of the nucleus itself and then the energy of the protons and the neutrons that are inside the nucleus, we notice that there is a difference. Well, that difference is called the mass defect. So the mass defect then has energy E equals delta m c squared, well, delta m is this mass defect. Let's now look at radioactive decay. There are different types of it. The first one is called an alpha decay, where the parent nucleus decays into a daughter nucleus and an alpha particle, which happens to be the nucleus of a helium atom. So first we have to remember that for any old particle, there is something we call an atomic number and something we call atomic mass. So the atomic number is the number of protons in that nucleus. The atomic mass is a number of nucleons, so the number of protons plus the number of neutrons in the particle, in the nucleus. So P stands for parent. I'm not going to use a specific example of a chemical element. So if I have a parent nucleus, it can decay into a daughter nucleus plus an alpha particle, which is a helium that has 2 protons and 2 neutrons in its nucleus. So then we may have to make sure that there's a conservation of atomic number and atomic mass here. So in order for this addition to take place, we have to subtract 2 from the daughter particle. So we have 2 protons here plus Z minus 2 has to equal Z. And then from the atomic mass, we'll have to subtract 4 so that the conservation law holds. So this is what an alpha decay looks like. Then there's a beta decay. So the parent nucleus decays into a daughter nucleus like before, but now it also produces a beta particle, which is an electron, and it can actually also be a positron. So if we look at this equation, so we have parent particle decays into a daughter particle plus, let's say, an electron this time. So there is -1 and 0, so there is -1 protons. That means that we have to add 1 to the atomic number, but the atomic mass stays the same. If we're dealing with a production of a positron, then we're going to say that we have this thing. So positron would be +1 and 0. So then here we have Z minus 1 and A. So these are the 2 examples of the beta decay. Then there is the gamma decay, where a nucleus changes from an excited state into a lower energy state by emitting a photon. So this goes back to what we talked here about the energy levels. So a nucleus changes from an excited state to a lower energy state, and the equation for this would be an excited parent particle is going to go to P. Z and A stay the same because a photon does not have any protons. So the asterisk here means that we're starting out in an excited state, and then we're going to a lower energy state by emitting a photon. There is reverse beta decay, where there is an electron capture. So let's see, if we have any old particle, then we add an electron to this. This is the capture, and we end up with some other particle that has Z minus 1 and A. So this is what we call the reverse beta decay. Now, we have to consider exponential decay, where we have to define some terms like half-life. So half-life is the time for half of a radioactive sample to decay. And then we have to define the activity of a sample, which is the decrease in radioactive nuclei per time. So delta N is this decrease in, delta N is the decrease in radioactive nuclei per a certain amount of time, delta T. Well, this activity is related to the number of nuclei that remain by this relationship. So the activity of the sample is equal to the decay constant lambda times the number of nuclei that remain. And that number that remain is equal to the initial number times e to the negative decay constant times time. So that's where exponential decay comes in, because we're dealing with an exponent here. And the half-life is related to the decay constant. So T half-life is related to the decay constant by log 2. So T half-life is log 2 divided by the decay constant lambda.